Hi everyone, my name is Justin Pirtle and I'm a Principal Solutions Architect with AWS. And today I'm here to share capabilities with you for how you can use serverless scalable messaging services via Simple Notification Service, SNS, Simple Queue Service, SQS, and AWS Lambda to add scalable messaging to your applications. In today's session, we'll start with an overview of our messaging services, then dive deeply into event processing models and consumption patterns. We'll take a close look at how Lambda concurrency scales, and then dive into how best practices can be implemented along with error handling. And then finally, we'll wrap up with choosing your optimal messaging services and guidelines for consideration. Now, this is a 300-level advanced session, so while we will dive deeply into SNS, SQS, and Lambda, we will not cover what is serverless, what is Lambda, and many of the great messaging and event services outside of SNS and SQS today. So with that, let's go ahead and take a look at our core messaging services. First, we have Simple Notification Service. This is our pub/sub or publish/subscribe messaging service where a producer sends a message to the topic, which is shown here in the pink, and a topic has one or more subscribers that get pushed the message in parallel. So this enables a pattern we call fan out. Now a subscriber can choose to filter messages and only receive certain messages, and subscribers can range from a variety of protocols, including email, SMS, mobile push, and what we're going to focus on today, Amazon SQS and AWS Lambda. Simple Queue Service, SQS, on the other hand, is a durable, scalable message queue that can support any volume of messages, and producers can push at virtually any rate. But once the messages are in-queued into a queue, one or more consumers polls the queue to receive those messages and can receive a batch of messages at the same request. Now what we have with SQS, by default we have what's called at least once delivery, meaning that we have the ability to receive messages and guarantee they're read at least one time. And this is implemented via what we call visibility timeouts. So when you have a consumer poll the queue for a message, we then basically have the message go invisible, though not deleted from the queue. And as soon as the poller and the consumer finish processing the message, they delete it from the queue with the delete API. If they fail to process the message or fail to call back to delete the message, after that visibility timeout expires, the message is visible again and will be picked up by another consumer. Hence we call it at least once. Now in our case today we'll be looking at AWS Lambda as the consumer of the queue, and the Lambda service will long poll the queue on your behalf. Finally, I want to mention that these are not mutually exclusive offerings, and you can actually chain the two together. So we can have an SNS topic have SQS as a subscriber. So in this example, we have two SQS queues, both receiving messages fanning out the processing from the SNS topic, and then allowing their ability to buffer them in the queue and guarantee the at least once delivery for each independent processing pipeline that's now fanned out. So we'll take a look at this closer in our session as we go. So now that you've seen an overview of these services, I'd like to take you deeper into how Lambda and serverless event processing works when paired with these messaging services. First, it's important to know that Lambda has three different invocation models. We have synchronous invocations with API Gateway, where API Gateway makes a synchronous call to Lambda and blocks awaiting a response from Lambda before responding to the client that called it. With asynchronous invocations, it's a fire and forget model. So with services like SNS or Amazon S3, we then call Lambda and we say, here's the message. And as soon as Lambda says, I've received the message, then they immediately return back to their clients and we say, hey, I sent your message. There's no awaiting of the processing, there's no blocking for the full process to finish. And then finally, we have poll-based invocations, which is what we have with SQS, Amazon Kinesis, and DynamoDB streams. And in this case, the Lambda service polls on your behalf the SQS queue or the Kinesis stream, And if and when there is a message in the queue, only then does it invoke your code for your Lambda function to run. So let's actually take a closer look at SNS to Lambda and that asynchronous invocation I mentioned to see how it looks. So in this example, you'll see here we have an SNS topic where we have sent a message indicated by the purple box, and that is going to the right-hand side to our Lambda service, where that message will go to the various subscribers in parallel. Now in this case, we have 3 different subscribers all subscribed to that topic, 3 different functions. But only 2 of the subscribers will receive the message because they have a no filter policy or a filter policy that matches the pattern of the message. In this case, function C is also subscribed, but its filter policy does not match the message payload, so it didn't get the message. Now if we look under the covers, there's a little bit more going on here. So to enlarge what the internals of the Lambda service look like, you can see on the right now, and for the duration of this talk, anytime we have this white Lambda border and box, everything inside the box is a part of the Lambda service, an internal component or feature of the service. And anything outside the box is something external to Lambda. So in this case, the topic on the left is in your account where we publish the message. Lambda is the subscriber, so we receive the message in a Lambda internal queue. So Lambda drops this in a queue that it manages. And from that queue, Lambda runs a managed poller on your behalf. So the poller pulls the message from the queue and looks at the message and can tell that the message is for function A, and we have another message for function B. Both were in queue. So the poller invokes creation of your sandbox environment or your function instance environment, where function A and function B both get the message. Let's contrast that with SQS now. So with Amazon SQS as the event trigger to AWS Lambda, you'll see that the picture looks largely similar, except now the SQS queue is in your own account on the left-hand side of the diagram, and the poller and all the other infrastructure is the part that Lambda manages on your behalf. There's no Lambda internal queue in this case. It's your queue, your SQS queue, that's being polled. So we have the poller, which we've seen before, but another key important feature is Lambda supports batching when interacting with SQS. So as we can see here, we have 4 messages in the queue. Lambda long polls the queue and pulls a batch of 3 out of the queue. From there, the poller takes the batch of 3 and can go ahead and invoke a function instance or a worker environment on your behalf, and you get 1 invocation of your code and your function environment per received batch. Now because we still have more messages left in the queue, the poller in parallel will keep polling and get the additional batch and spin up another function instance with another invocation. So we continue scaling out while the messages are processing in parallel. Now eventually the first batch, the batch of 3, finishes, and in this case it was successful. So on your behalf, the Lambda service calls the delete message batch API. So all 3 messages are deleted, and the additional batch is able to still process. Now the function instance that was created, it's not disregarded automatically. It sticks around in case there are other messages that are needed to be processed in the near term. Eventually, if it's idle for a period of time, it will be recycled. But in this case, let's say that one message in the batch, the other function instance, it actually fails to process. Well, this is where the concept called visibility timeout comes in, because Lambda stops processing, and you can see the gray icon down there on the message in the box with the clock. The clock is indicating that it's invisible and the timeout is dwindling. So once that visibility timeout expires, then the message pops back to life as a normal message and is ready to be picked up again, where the poller will grab it again. So in this case, we have the message D, which is picked up again by the poller, but now we have a receive count of 2. And so that's the main difference here. Now, how we handle this error condition, we will address shortly later on in the presentation. But first, let's take a look at Lambda concurrency and scaling. And with Lambda concurrency, with SNS as the topic, as you being your event source for Lambda. The key thing to know is every event is one invocation for your Lambda function. It's a fire and forget, so you're able to scale out in parallel to the number of events coming in. Whereas with SQS, each event is in-queued in a queue where they can be buffered and rate limited. And you have the ability to have batching. You can pull off a batch of up to 10 messages at a time for processing together. And you have the ability to actually rate limit this consumption. So why is that important? With a service like SNS, let's say you were sending messages too quickly. Well, if you're actually sending them so quickly, what if you have an issue with a downstream system like a relational database? In this example, we have 3 function instances shown, but imagine it were 300. 300 independent connections could be going on to that relational database. You could overwhelm the connections and basically implement back pressure where that service could fall over. And so for these reasons, there's a powerful benefit when Lambda is paired with an SQS queue to be able to rate limit the function consumption. And so what we can do here is we have the ability per function to control concurrency. And we have a feature called reserved concurrency, which acts also as a current concurrency ceiling in addition to a dedicated portion of a concurrency pool allocated for that function. So this concurrency ceiling, if set, enables us to cap the concurrency at the speed and rate at which we drain the queue. So as you can see in the chart below, our concurrency scales up to 5 because we have it set to 5 as our reserved concurrency. And at that point, even though we have more messages in the queue, we actually just see the throttles increase because the polar is getting throttled back because we've set this concurrency ceiling. And only after the throttles decrease, because the concurrency is freed up again, we finally get through the queue, do we actually see our concurrency go back down to under 5 when it's no longer needed. So this would ensure that we don't overrun that relational database. Now visually, what this could look like is a variety of spiky traffic coming in, scaling up rapidly. But from your functions perspective, very steady state processing on the back end with no issue. The final consideration from a scaling perspective with Lambda is the polar itself. So as I mentioned, Lambda runs a polar on your behalf, and it starts with concurrent batches of 5 invocations at any moment. But if those invocations are running and there are more messages remaining in the queue, then we do an additional 60 invocations each minute afterwards, scaling all the way up until we either have drained the queue or we reach 1,000 maximum concurrent invocations. Assuming a max batch size of 10, this means a single function paired with an SQS event source could be processing 10,000 messages concurrently in parallel. And so that's just a quick look at the scaling. But another key consideration for SQS for many applications is the concept of ordering, and particularly strictly ordered FIFO processing. So what is FIFO? FIFO means first in, first out. And with the standard SQS queue, you would have best effort message ordering, meaning that your messages generally will be in the right sequence, but they could be delivered out of sequences in some circumstances. You also have at least once delivery, as we've shown so far. With a FIFO queue, you have strictly preserved message ordering, and you have the ability to implement exactly once message delivery. Use cases where you'd want to use this would be things like order processing, ticket booking, inventory management, or financial trading. But why would you not always opt for a FIFO queue? Well, there is a trade-off in the throughput and at the cost level. There's a slight difference in the cost of both and the throughput, so you want to be mindful of that when choosing. But let's see how exactly this works. So as we saw before, here's an SQS queue with our Lambda infrastructure. We're able to pull out a batch of messages, the polar picks them up, and invokes a function instance, 1 invocation per batch. But in this case, if we need strictly preserved ordering, message D cannot be processed until the first messages are finished, if we assume that all messages should be treated equal and ordering must be guaranteed across all messages in the queue. The reality, though, for most customers is not all messages need to be ordered and have the same guarantee equal to each other. There are subgroups of messages that could be where ordering guarantees are needed but could be broken off separately. And for this we have message groups. And so just to take a look at how it looks with message groups, in this example now, one queue, but we have 3 virtual message groups. These were grouped by passing in an attribute called message group ID. And in this case we have a group A, B, and C. And now that we have 3 different message groups IDs, the poller is able to go ahead and long poll again and get a batch. And notice that that batch actually spans messages from 2 different groups. This is what we call a heterogeneous batch. So we're able to go ahead and grab multiple groups of messages off the queue and start the function instance processing that batch. From there, we have another group, group C, that has no messages in flight. So because it's not waiting on something else to finish, the poller can spin up another parallel instance of your function, and we can process that batch. But at this point, all 3 message groups have messages in flight indicated by their visibility timeout dwindling and the gray icons. So until the messages in flight finish in one or more of the groups, we could not process any further and maintain the ordering. So let's assume the first batch finishes successfully. Then Lambda calls that delete API on your behalf, and now we're free to grab the next batch of messages just as before. So with this, that takes care of ordering, but it's important to think about delivery. And so we have this additional concept with the FIFO queues of exactly once delivery. And it's interesting, I say that SQS gives you the ability to have exactly once delivery, but the reason for this is it gives you the mechanism to implement it. It doesn't guarantee it by itself. You have to be cognizant of this scenario where your consumer could get the message, but either fail to send an acknowledgement or the acknowledgement never be received by the sender, and by SQS in this case. And so you still need the ability in a distributed system to have idempotent processing, handling duplicate messages without processing it more than once. But SQS FIFO gives us this ability, and let's see how. Here is what a Lambda function with SQS FIFO actually receives. We have a records array with multiple messages, up to 10. In this case we have 2, each one object. And you can see each message has attributes. So we have the body, and we have additionally these important attributes of message group ID and sequence number. So from an ordering perspective, if we need strictly preserved ordering, we want to group by message group ID and sort by the sequence number inside our code and make sure to be cognizant of that. Because if we did something like a for each, where we just process them with a for each on the entirety of the array, we could easily process them out of sequence. So it's important to keep this in mind. Now from a delivery perspective, we have one additional attribute called deduplication ID. In this case, message deduplication ID. And so what happens here is when you finish processing the batch of messages, as you process them successfully, you would checkpoint your processing with the deduplication ID to a separate state store of your choosing. And then when you receive new messages, before you process them again, you would first check if that checkpointed ID already exists. If it does, you would just simply ignore the message and return success, not processing it twice. But what if you also need in your application ordered fanout? Well, I'm pleased to announce that as of the last month or so, we now have SNS FIFO topics. So the same first in, first out guarantees with strictly preserved ordering, exactly once delivery, through message group IDs and message deduplication IDs are all present on SNS topics as well now. The same throughput constraints apply to both SNS FIFO and SQS FIFO as well. So putting all this together, a reference architecture for a FIFO application might look something like this. You first send a message to API Gateway, which could have a Lambda function acknowledge the order, generate an order ID, and send it to a FIFO topic. That FIFO topic could fan out to SQS FIFO queues, at which point our inventory management FIFO queue could decrement the seats for the concert that you're selling quickly and guarantee in the rare event we oversold a seat that the first order received would get that seat and not the second. And in parallel, we want to also process the payment to free up any seats that aren't needed if the payment fails. So we could have our payment processing proceed in parallel, ultimately having Lambda consume these events and write to DynamoDB. So that's an end-to-end FIFO application as a reference. Now that you've seen an application end-to-end and all of these semantics on processing, I want to take you deeper into best practices and potential error conditions that you want to be mindful about. There are two types of errors that you should be conscious of. One is an unexpected event that cannot be processed by your code without throwing an exception. This is what we refer to as poison messages. And this would cause your error to occur inside your function, throwing the exception inside your code. Now additionally, we have system level errors, particularly things that should be expected, like Lambda throttles. So let's take a look at each in our various scenarios. First, with SQS, let's look at what happens if you have a poison message. So we send a message to the queue. The queue is able to pull off the batch of messages, say our batch of 4. We send them to the poller, just as before. We get a function instance created. And inside that instance, let's say one of the 4 messages, message B, is a bad message. Well, message A, C, and D can finish processing successfully, but if we throw an exception the moment we see D, even if the others finished processing already, what Lambda would do is stop processing, not retry, and not call that delete message API at all. And in this case, what will happen is we need to wait for the visibility timeout to fully elapse, and only after that timeout elapses do these messages become visible again and picked up by Lambda. And so you can see our receive count is now equal to 2 since they've been received more than once. Well, if it's a bad message that can never succeed, this process could continue indefinitely if you don't set something called a redrive policy. And what would happen is it would continue in a cycle indefinitely until the message expired from the SQS queue. So the default retention period would be 4 days, or the queue could be configured to keep messages as long as 14 days. But once that would hit, the message would just be gone. Now you don't want to waste all that time processing a dead message. So as a best practice, we always recommend using redrive policies. And what this does is it allows the SQS queue to know the max attempts or receives that should happen per message. And when you reach a max receive count, write the message over to a dead letter queue. In which case, at this point, if all of the messages in the batch were all tried at once and failed at once, the entirety of the batch would go to the dead letter queue. So here we have the receive count of 2, and you can see that all of the messages were moved to the dead letter queue in conjunction. And so what this means is all of those messages, even though 3 of the 4 were processed successfully, were all disregarded together. Now once they're moved to the dead letter queue, it does mean that we can process additional messages without any issue or needing to spend more time on the others, and they can be reviewed manually or automatically processed from the dead letter queue in conjunction. Let's see how this scenario changes if we actually delete messages ourselves before throwing that exception. So we'd start the scenario the same. We get the batch of 4, we go through the poller, we start the function instance, we have our variety of messages, but in this case, B had the error again, but before we return the error, let's say we catch the exception, and we actually finish processing A, C, and D, which succeed, and we called batch delete, saying A, C, and D should be deleted, all before we return the exception. Well, now our delete call goes through, we finish that, and we return the exception, and B is not retried automatically. So just as before, we wait for the visibility timeout, the message B comes back to life, and at that point, we can go ahead and pull message B. So message B goes up through the poller, right? But we don't have to wait on anything else. And we didn't, even if we go to the dead letter queue, we only discard message B, not other messages that could be processed successfully. Next, let's take a look at how the system level Lambda throttles work with SQS. So in this case, the poller pulls a batch of 4, goes to the poller. The poller tries to spin up the Lambda function instance, but it receives a throttle event back from Lambda because you've hit a concurrency quota. Maybe it's that reserved concurrency you intentionally set on the function. In that case, the Lambda poller stops scaling up, knowing it's already hit its limits, and retries processing the messages that are buffered locally at the poller until the remaining visibility window on the messages, whenever that is no longer greater than the function timeout set on the function. Only at that point does it stop retrying. And at that point, we would basically give up and wait for the visibility timeouts. But in this case, most likely it will succeed, in which case we'll actually go ahead and have all the messages end up processed successfully in the function instance. It just may take slightly longer. So this goes to illustrate that you shouldn't fear throttles. You just want to be mindful that it means things could take longer to finish, but all the retrying is done on your behalf. And throttles in your metrics are not really a bad thing, especially if you've intentionally configured a throttle on the function. So with that, let's quickly look at SNS to Lambda, the first scenario being a customer issue in a function due to a poison message. So we send a message to the topic. The message goes to an internal event queue, which goes to the poller, which tries to spin up the instance, but let's say the instance actually throws the exception. Right? In that case, just as before, Lambda doesn't retry from the poller directly. The message goes back to the queue with its visibility timeout, and this is the internal queue of Lambda. And so that timeout elapses, and then the poller picks up the message again and retries the function again. Well, assuming the message is a poison message, it will likely never succeed. So Lambda allows you to configure up to 2 additional retries for a total of 3 attempts, including the initial attempt, before it will actually either discard the message or send it to a dead letter queue or an on-error destination of your choosing. You have the ability to configure both the max age of the message and the max number of retry attempts. If you do set up that dead letter queue, what happens is the poller would actually write the message to the dead letter queue on your behalf, and that way you wouldn't lose it and could actually review it later on and alarm on this queue. Now in the other scenario of a Lambda throttle, in this case we send a message to the SNS topic, goes to the event queue, goes through the poller. That tries to spin up the function instance, but this is where we get throttled. So in that case it's similar to before but slightly different, where the poller will retry on your behalf. But in this case, it'll retry until the max age setting on your function is set or 6 hours is reached, whichever is less. That will determine when the poller will give up. And just as before, if it's tried more than once and it has to give up, then it can go ahead and discard that message into a dead letter queue or on-error destination of your choosing. And so we highly recommend always configuring a dead letter queue on any SNS or asynchronous event source, because that will ensure you never lose a message. So to summarize these best practices, I want to briefly touch in the various areas. On the queue level, we've mentioned the visibility timeout is a very important setting. And so to allow Lambda to have time to retry those messages on your behalf, you want to set the visibility timeout to 6 times the function duration. This will avoid having that receive count increment up unnecessarily and sending messages to the dead letter queue that could be processed successfully. Now on the function configuration level, it's recommended to always use batching for cost savings and performance gains. But if you use batching, it's important to understand the exception behavior and to ideally catch your errors together and return them all at once you've processed any possible message that could be finished successfully. If they did succeed in the batch, delete them yourself from the API rather than wait for Lambda to retry them and fail the entirety of the batch. You could go ahead and delete the ones that succeeded and then just return the error on the ones that didn't succeed. And if you want to speed up the processing of the failed messages, you can also change the per message visibility timeout inside your code for those messages to a low value before returning the error, which will allow them to be nearly immediately reprocessed. But the most important thing to keep in mind is you want to understand your function error metrics and be monitoring that, because even a fraction of errors will make the poller believe that it's encountered back pressure, and it will not only stop scaling up, but it will scale down the poller concurrency, limiting the speed at which you can drain the queue. For a few additional best practices to recap, as we've mentioned with Lambda FIFO processing, you want to group and sort the messages in your code in that array before you process them. And you need to be doing item potency processing by checkpointing with the message deduplication ID. With SNS Lambda processing, because it's an asynchronous event source, it's extremely important to configure a dead letter queue or an on-error Lambda destination inside the consumer, the Lambda function itself, and have that so you don't lose messages. And then optionally configure filter policies if only certain consumers need messages and others do not. Finally, because SNS Lambda doesn't have batching and one message is one invocation, it's important to monitor your concurrency quota and make sure it's high enough to allow the concurrency to scale out to any burst of messages received. Now finally, to wrap up, I'd like to share a simple decision tree with you on how to choose between these services for your use case. So the first question to keep in mind is, do you need fan-out? If the answer is yes, and you need to send messages in parallel to multiple subscribers, then SNS should be part of your architecture when looking at these services. The follow-up question to that is, do you need rate limiting? So if we go down the left path of this tree, assuming you also want to rate limit for downstream consumption to not overwhelm resources, then SNS paired with SQS is a great combination. But if you just need fan-out and don't need rate limiting, then SNS by itself should do, with Lambda as its subscriber. Now going to the right side of the tree, let's assume we don't need fan-out, and SNS is not needed in this case. But if we do still want to rate limit the consumption speed of the messages, that's where SQS comes into play. And then if you don't need rate limiting or fan-out, then perhaps the easiest option is just to invoke a Lambda function directly, either synchronously or asynchronously to meet your use case. With that, I'd like to thank you for joining today and hope you consider SNS and SQS and Lambda in your next application. I'd kindly remind you to please complete your session survey because your feedback means a lot to us. But thank you again for joining today.